In this video, we're looking at further sign diagrams. Now, what I mean by this is we'll be drawing sign diagrams of f, f dash, and f double dash, all three. Now, we can use this little table to help us do this. So basically, these things here on the left are the numbers you put underneath the sign diagram. And then to get the pluses and minuses on the sign diagram, you use this stuff on the right. So hopefully that'll make sense when we do this example here. So there's our function. We need to draw a sign diagram for all three bits. So I'm going to start just by rewriting out our function. So that is x cubed 2x squared, take x, take 2. We will get our derivative, which is going to be 3x squared plus 4x, take 1. And we're going to get our second derivative, which is going to be 6x plus 4, just like that. Now we need to do sign diagrams of each thing. So the reason that I've sort of spread them out like this is so that we can look at our sign diagrams. So that top one will be f. We'll then do another sign diagram for f dash of x, and then another sign diagram for f double dash of x. Now, just a reminder, the things that go underneath this sign diagram here, according to our table, were the x-intercepts. And then the thing that goes up to tell you whether it's plus or minus was the above or below the x-axis. Now let's pretend we didn't know that. I'm going to show you a cheeky trick to basically cheese all the sign diagrams. Essentially, x-intercepts is another way of writing f of x equals 0. In fact, no matter what sign diagram we do, this one for example, we're going to be looking at f dash of x equals 0 to get those numbers, or f double dash of x equals 0 to get the numbers on this one. So let's do that. Easiest way to solve this equation is polysolve. So if we have a look at this, we will go to equation mode. I'm going to polynomial, so that's going to be f2. It's a degree 3 because 3 is our highest power. And the coefficients are 1x cubed plus 2x squared minus 1x, take 2. Solve that, you're going to get 1 minus 1 and minus 2. And that's exactly what I'm going to be putting on my sign diagram. Now, I will point out 1, minus 1, and minus 2 are also your x-intercepts. Now, the reason I show you the polysolve method is because that just always works. Sometimes it's a bit tricky to spot like points of inflection, for example, or x-intercepts. But if you want, you could have had this graphed. So we'll just have a look at the graph there, draw that, and I would have got the same thing if I'd done root to find the x-intercepts, minus 2, minus 1, and 0, and 1. So now we need to figure out if it's above or below the x-axis. I'll remind you that you can pick a number like, let's say 0 is in this range, sub it in there for x equals 0, you would get f of 0 being minus 2, and that would tell us that this would have to be a minus sign up here. But what you're probably more likely to do is look here, in between minus 1 and 1, the whole function is underneath. That tells you that it's a minus sign there. Similarly, after 1, so everything's sort of out here, the graph goes above the x-axis. That tells you it'll be a plus sign. And then in between here, it goes above and it goes below like that. And that's basically just using the table up here. When it's positive, our function is above the x-axis. When it's negative, we're below the x-axis. So that's how we figured that out. All right, let's do the same process for our next sign diagram. So again, I might just polysolve this. So we'll go back into menu, go into equation mode. Polysolve, we've now got a degree 2. Now you could use like the quadratic formula or something, or sum and product, but polysolve's pretty quick. So we're going to do that. And I'm very glad we polysolved it because we got horrible numbers. 0.215, let me make sure I've got that 100% right. Yeah, it looks pretty good to me. 0.215, so that's going to be our first one. And I'm going to make really sure to make sure that number is in between minus 1 and 1 visually. So halfway through there would be 0. So 0.215 is sitting about there. And I probably shouldn't have put that little dash on the sign diagram. There we go. All right, the other one is minus 1.548. So again, that's got to be between 1 and 2 on the one above it. And guess what? Those numbers there should correspond to our minimum. So that should happen at 0.215. There it is. And the other one was minus 1.548. There we go. Wonderful. Let's actually check that on our graph. So if we go graphing here, draw it, and I go Shift G solve minimum, yes, I do get that. And if I go draw it again, Shift G solve max, yes, I do. So that's right. Very good news. I will point out that you can use your calculator to get x-intercepts and mins and maxes, but if the graph instead had looked something like there, and we wanted to find our x value for that one, your calculator can't really find flat bits like that. So that's why the polysolve method is good. All right, 6x plus 4. Oops, sorry. We got to put the pluses and minuses in first. So it's sloping up before minus 1.548, so that's a little plus there. It's then sloping down in between those 2 points. So it's a minus, and then it's sloping up again after. So the thing that we put on the bottom of this one was your stationary points. They're the numbers that go on the bottom here. And the slope up or down is how we filled in the pluses and minuses up the top there. All right, next one here. F double dash of x equals 0 are your inflection points. Might type that forward, inflection points. And then we're going to be using the concavity to tell what's going on up here. Now, if we try and polysolve this, your calculator's not going to like it because this is a degree 1. So basically what we can do here is we can solve 0 equals 6x plus 4. This is what your calculator is doing when it does a polysolve. So minus 4 is 6x, therefore x is minus 4 over 6, or in other words, that's minus 2/3. All right, now let's make sure we get this in the right spot. Here was minus 1. I go down from that, minus 2/3 there. All right, that should line up with an inflection point. And if I maybe go to my graph here, and I go Shift Trace, and I type minus 2/3, it looks like that point is highlighting this inflection point, sort of like there, essentially. So that's good. And then it's concave up and concave down. Now, basically what those things mean, concave up will look like a smiley face, and concave down will look like a sad face. You just got to be really careful, because anything like that on a graph will be sort of concave up all the way through there. And then all the way after that, it'll be concave down because it's made a sad face. So with the graph that we've got, it's concave down first before that green point, and then it's concave up. So it's going to be minus plus. There we go. We've got all 3 sign diagrams. Now we're going to do the rest of these questions. Find and classify all the stationary points. So we've already sort of noted that the stationary points were these 2 numbers here on f dash of x. So the stationary points happen at minus 1.548 and they happen at 0.215. You can sort of tell from the sign diagram here what they are, because it slopes up and then down, that would be a maximum. And when it slopes down and then up, that would be a minimum. So this first one, when we find out the y value, is going to be a local max. And this one will be a local min. And you can check this from the graph as well, because on the graph itself, it's a max then a min. So if I go, I could trace minus 1.548, or I could just G-solve the max, and I get 0.631. For the local minimum, we can do that as well. So we can just go Shift G-solve min to minus 2.11. Where is the function increasing and decreasing? So the function is increasing wherever there's pluses on this slope sign diagram here. So it's increasing before minus 1.58. And it's also increasing after 0.215. it is decreasing for x in between those two numbers. So that was using the middle sign diagram. So this one here, because sloping up is another word for increasing. All right, wonderful. Find and classify all points of inflection. So the points of inflection are on this bottom sign diagram. So one of them, well, the only one of them is going to be minus 2/3 for the x. And we can go into our graphy graph and go trace minus 2/3, and you'll get y is minus 0.740, or 741 essentially. Now, I have said that we probably shouldn't play with fractions and decimals at the same time. That was the y value on the graph there, and if we hit s to d, we should get minus 20/27. Cool. Now, what type of point of inflection is this? There's two types. You've got non-stationary, where it's not flat at the same time, or you've got stationary, where it's flat. You can tell from the sign diagram. You can see here we've got a point of inflection, but at minus 2/3, we don't have a stationary point. That would tell us this is non-stationary, because it's, well, not stationary. So that's how we classify this one. If f dash of x did equal 0, then we would have a stationary point. And I'm pretty sure we can agree that green point is not flat, it's sloping down. Last one, classify when it's concave up and concave down. So we can use this sign diagram here to tell us it goes minus and plus. So it's concave down for x less than or equal to minus 2/3, and it is concave up for x greater than or equal to minus 2/3. Done. All right, now I have got a question to you here. I'm not going to go through the whole sign diagram because this would be a nasty quotient rule to divide that, but we can do this visually anyway. So let's see if we can get sign diagrams of each of these. And the reason that I want to point out this one in particular is because we've got an asymptote. So how do we deal with that? So basically, this sign diagram here, I put in all my x-intercepts. So there's one happening there at 0. There's also an asymptote here happening at 1. So the way that you mark that is you put a 1 there for the x value. And that's just that point there where we're asymptoting. Since this is a sign diagram of f, we are below the x-axis before 0. We're still below it after 0 down here. We then swap to being above the x-axis when we wrap back around after that asymptote. We can do a sign diagram of f dash of x. So we've got to talk about the slopes here. So this point here happens at x is 2. So basically, after 1, I'm going to have 2 here. We still need to put that 1 there, because whenever you find these critical points, it's really important that you also put anywhere where the graph doesn't exist, for example here, or any points where like the derivative doesn't exist. And I believe there's another stationary point at 0 as well. So we use the slopes to fill in the pluses and minuses. So here it was sloping up, then after 0 down. After this asymptote, it's still sloping down, and then it's sloping up after 2. Lucky last. There are no inflection points on this graph, so we just have the asymptote at 1 there. And basically it's concave down before that and concave up after that, because it's a sad face and then a happy face after that. Wonderful. So to do this question properly, you would absolutely use the equation, do the quotient rule, etc., etc. But you can see you can almost get sign diagrams just visually from functions.